Okay, so we will proceed with the first talk from Eugenia Makarova on the use of machine learning to correct NWP model sea surface wind forecast with scatterometer data input.
It's a long one, yeah, I know.
So please.
Okay, so my name is Eugenia Makarova, and I represent here the satellites winds group from the physical and oceanography department from the Institute of Marine Sciences. So this is work that I'm currently doing, and it was also part of this work was my final master project at the Autonomous University of Madrid. It was the master in data science. So the objective of the work basically is to correct the persistent biases of the numerical weather prediction models. In this case, we are working with the numerical weather prediction model by European Meteorological Center. So there are several works that studied that there are some persistent biases for the stress equivalent winds that are present after the assimilation of the observational data, including the observational data provided by the satellites, by the scatterometer instruments. So there were many attempts to improve this assimilation. And we also had a previous project before this one that was called ERA-STAR that consisted in accumulating the differences between the scatterometer observations and the model outputs for like winds over the oceanic surface, and applying the corrections to the model output. So we decided that apart from the trying to correct the model outputs only based on the observations from the scatterometers, we could also try to create a regression that will be based on the model parameters itself, and the model would try to predict the persistent biases. So here we can see an example of the persistent biases they were accumulated over 1 month. It was for the whole February of 2019. So here's okay, where's the pointer? So you can see some of the biases that are caused by the convection processes in the tropics, for example. Some caused by the coastal processes, for example, there in the near the Panama. And some of those caused by the currents and atmospheric stability. So here's the concept of the model. Basically, we want to use as input parameters the location, the atmospheric stability parameters such as surface temperature, surface pressure, specific humidity, some oceanic parameters such as sea surface temperature, the gradients, and the currents, and some of the wind derivatives such as curl and divergence, for example, and gradients. So as it was the final master project, we tried to train the model on a small subset of data, so it's not like a global model at this time, but we are still continuing the project to create something more operational. So here we just try to show that this approach actually is valid, so we can do this. Here I will make a little bit the introduction about the previous project that was based on on applying the biases based on the observations by accumulating them over a large period of time. The nominal project was accumulating the differences in a 15-time window, and the mean differences are further applied to the model. So here we were able to reduce the error variance by 4 up to 7% globally, depending on the scatterometer constellation that was available for the certain year, because we generated a 11-year product, and the scatterometer constellation was different per each year, basically. So our observational data they had different sizes and the sampling. So the problem of this approach, it has several limitations. So it only captures the biases that are very persistent over several days. It is very sensible to the scatterometer sampling. So when we have the gaps in the scatterometer sampling, our metrics, they go down and they're getting worse. So we can't see the dependence between the atmospheric and ocean state condition and the errors. And it also showed that there are limitations in the operational use. So we had to use the temporal windows that are quite larger, and the performance was worse than in case of the reanalysis products. So I will tell about a little bit the observational data that we're using. It's the satellite data that goes from the scatterometer instruments. So the scatterometers are the instruments that emit electromagnetic waves to the surface of the planet and receive the backscattered signal. And from the backscattered signal, we can infer basically the wind intensity and the wind direction. And we are using the instrument that is on board of a METOPAY satellite for training our model. And basically this satellite passes at 9 a.m. and 9 p.m. local time every day. So we have only local coverage 2 times a day. And the repeat cycle is about 29 days. So here we can see the example of the swaths of the scatterometer. Basically, it has 2 swaths at the same time. And the resolution that we're working here is the 12.5 kilometer grid. This instrument is also not very, well, the rain doesn't affect it very much compared to other scatterometers. So it's an advantage for us in this case. Here we can see the daily coverage of this scatterometer, the descending orbits. And so the target that we're using to train our model, basically, those are the differences between the zonal and meridional components, between the scatterometer observations and the ERA5 reanalysis model by the European Meteorological Center. We're using only 3 months of data in this case, in the preliminary project. And we have split it into train, validation, and test subsets. So from the ERA5 reanalysis dataset, we're using the stress equivalent wind components, also the wind speed and the direction, the sea level pressure, temperature, specific humidity, and the sea surface temperature. We convert also the neutral 10-meter winds into the stress equivalent winds, so they are more aligned with the scatterometer winds. For the currents, we're using the data from the global total surface current from Copernicus, and we also calculate the derivatives such as wind curl and divergence and the SST gradients. This is the example of our training data set. So we can see here the mean biases for the whole training data set for 2 months and several days. It was January and February 2020. As you can see, the biases are very similar to what I've showed you before for 2019. So it's another year, basically. And the biases are quite similar for the same period or for the same months. So it was for the zonal and for the meridional component. So for the first step of the project, we used the point-per-point approach. So we didn't use any special convolutions. And we tried the algorithms that are based on the ensembles, decision tree ensembles, the gradient boosting algorithm by XGBoost, and also the simple feed-forward networks with several hidden layers. Well, we tried to implement them with different libraries, and currently working with PyTorch library. So in the second stage, we also tried some convolutional neural networks, but so far we didn't get better results than for the feed-forward network, but it's a work in progress. So to prepare the data, we had first to collocate the data in space and time. We have like 2 model outputs, and we also have the scatterometer observational data. We had to calculate the derivatives for the inputs, to normalize the data for the neural network models, and we split the data into 3 parts. Also, to reduce a little bit the training time, we used random downsampling. So I think in that case, we took like 5% of the total data because the data has high resolution, but it is quite repetitive. And now I'm using like 10% of the subsampling. So the metrics that we're using in this work is basically vector root mean square differences, that is root mean square error for width components, includes both of them, and the relative error variance reduction. So we did two types of validation. First, we left apart 25% of the data for the test subset, and that was collocated to the same scatterometer that we used in the training. And the second type of the validation was to generate the corrections for the global numerical model fields, apply those corrections, and collocate them with the independent scatterometer, HY2B. So yeah. In that case, we used a slightly different period that includes the days from February to end of April. It contained part of the training period and part of the test period. And the good thing about collocation with HY2B that it has 3 hours and 3.5 hours difference in time from the passes of the ASCAT. So in this case, we're actually testing the numerical correction, the corrections for the numerical model for other local times, not the same as collocated with ASCAT. So here we can see the results for the ASCAT test subset. We tried 3 configurations with XGBoost with 500, 1,500, and 2,000 trees. We also tried the MLP regressor from sklearn, and we tried the implementation with TensorFlow with 4 hidden layers. And we basically stayed with the configuration of 256, 128, 64, and 32 perceptrons per hidden layer. So the models that are selected here in red, we've run the validation against the independent scatterometer. So here we can see also that for the training data set, we can see that the XGBoost, extreme gradient boosting, it looks like that it can be overfit into the data. So for the training subset, the results are quite similar for the neural network models and for the gradient boosting trees. After that, we did the validation against HY2B. And here we can see that globally, we reached the reduction up to 5 and 54% of the error variance. And for tropics, we got the reduction a little bit worse than in our previous project, ERA-STAR. And the best performance was in the extratropics, when we reached the reduction of the error around 7 and 66%. I've also run the similar validation for another year for the similar period that we used in training. So these results are for 2019, and the training was done for 2020. And we can see that we also reached the reduction for extratropics around 10% of the error variance, and globally around 6 and 63. So here's the example of the model outputs. We can see the original error 5 field for zonal component on the left top. The ERA-STAR is the model that was based only on the observations. It's in this case, the differences were accumulated over 15 days. So they're quite smooth in this case. And at the bottom, we can see the output of 2 models. One that is based on the convolutional neural networks that is used for super resolution tasks. And on the right, it's the output from the feed-forward neural network, which I showed the metrics previously. So we can see basically that the patterns are quite similar for the model, for the corrections from the observational data and what we generate with our model. So here is the comparison with the biases accumulated over 3 days compared instead of 15. So we can see, for example, that the CNN is more similar with the 3-day output than 15, and they feed forward with 50. So it's like the corrections are smoother. So we made an analysis, a special analysis of the errors. Where we, well, on the right, we can see the errors of the error 5, the quadratic error. So we can see that the errors are quite high in the tropics. And we can see basically that in the tropics, with our model, in some of the zones, the green is where we we have the better metrics in error 5, and the red is where we have worse metrics than error 5. So we can see that in some zones, we actually correct the model quite well, but like in the tropical convergence zones, we're not correcting it that well. So we still need to find out how to deal with this problem. And well, as we're using also like extreme gradient boosting, the decision trees, we also could see the feature importance of our inputs, and this we can use to exclude the parameters that are not that important to make our model more robust. This is not that evident when we're using the neural networks directly. The problem with this analysis is that we have seen that a lot of our inputs, they are very correlated between them. So some of the model inputs such as pressure or air temperature, humidity, they have very high correlations, as you can see here. So as the conclusions, we can see that even training our model on a very small subset of data of about 2.5 months, we were able to reduce the errors by 66% globally and about 10% in extratropics, even when we validate with another year. So if we train the model on larger subset, probably we will be able to use it for operational purposes to reduce the model errors. And if we use the model corrections for the training period, we can also enhance the reanalysis products and also to correct the products for the periods when we didn't have any observational data. So this is it. Thank you very much for your attention. And if you have any questions, feel free.
And afterwards we have a discussion time to get deeper in more scientific or more deeper questions. Some question, small question. Peter.
Thank you for your talk. Perhaps the last slides has been passed very fast. And which are the important variables for predicting the biases?
So we have a lot of ways basically on the position of the point for which we're making the prediction. Also the wind direction, in this case, the components, the specific humidity. So yeah, the thing is, the order, yes, so the big ones. So the problem is that some of those are very correlated, so you can't take them apart from
Any question more? Yes.
Hello. You use Northern Hemisphere winter data to train your dataset, the network. Do you think that introduces a bias?
Sorry, could you repeat it?
That for the training, you use what was data from the Northern Hemisphere winter, and then for the validation, the testing, you were using the rest of the data. So do you think that using seasonal data introduces some bias?
I'm not sure if I will answer it, but so we're thinking now to split the model into like to train the model for January, for February, like for several months. So it has like a seasonal part. But I think I also can include like the time parameter inside the model. So also to generate the prediction based on the like the time of the year. So I'm not sure if it answers.
Just to clarify, so we are using a month specifically, yeah, which as Eugenia says, we will do that for different months, of course, and that's the idea. But this is done like locally at every point, everywhere in the global ocean. It's just that we use a subset because we have computational efficiency problems, yeah, which we're not dealing with. But this is done everywhere, yeah.
Last short question.
Thank you. It's a curiosity, when you project your results, you seem to have a mask for the polar areas and the Mediterranean. Does it have any reason or? You're not projecting in those areas.
Well, we don't have any observations over ice, over land, so it's only the sea surface where we have the observations. So basically, those are the areas where we're making the corrections. And also, I'm using currents as one of the inputs. So if I don't have the currents data, basically, I filter those areas as well because they won't be valid.
And the Mediterranean?
In the Mediterranean, the globe currents data didn't have any coverage, so we can focus only in the Mediterranean, I think, as well.
Okay, thank you.
Yes.
Any more questions? If not, let us thank the speaker again.
Thank you.